Hello, guys, and I'm back with the last video of this series, which heading has enthalpy of mixing and reactions. It's going to be a particularly short video. So yeah, so whenever you mix two things, if they're not ideal solution, it evolves or engulfs some heat. So we call that as delta H of mixing. Let's say you have some HCl gas and you pour it in water, some heat will be evolved. So what does this value of delta H mixing depend on? It depends on the concentration, the nature of solvents. Let's say you have HCl in water, then it will be good amount of heat. But when you mix heptane and hexane, there won't be much heat evolved. And then there's one thing called solvent by solute ratio. Wherever you have tables, you'll get all the values of delta H mixing in terms of solvent by solute ratio. That is one thing. So yeah, and it is, as I told, it's the units are kilojoule per mole of solute. Like if you're adding HCl gas to water, it will be kilojoule per mole of HCl gas. Let's consider one example. So here we have some specification that HCl at 100 degrees Celsius and water at 25 degrees Celsius entering, and number of moles are specified, and then you are getting some weight by weight outside, some concentration at 50 degrees Celsius. Let me assume 50, 40, anything is okay, but I'll assume 40. This is the exact example from the book. Check the spelling. Okay, so when you calculate R, what was R? This value I'm calling it a R. Okay, so R is 8.1. Number of moles of this by number of moles of this, you are getting R something around 8.1. So if you get the value of R, you are getting the value of R something around 69 kilojoule per mole HCl. So what next? You need to check out the reference. The reference here is 25 degrees Celsius. So what does this 25 degrees Celsius mean? That if some compound is at 25 degrees Celsius, then its enthalpy has to be taken zero. So what is the method to solve it? First of all, you make an enthalpy table. So yeah, this is all material balance is done. I'm just doing the energy balance part. So here the substance. Substance is HCl gas, H2O liquid, HCl aqueous. Okay, so yeah, um, one more is required. This is in, this is out. Sorry for the poor shape of the table, but please try to manage. HCl gas in would be 5480. This is 44400. This is actually 44.4 kilomole. 44400. Now you see, this value is at 25 degrees Celsius, so enthalpy. This is H cap, this is N, this is 0, N, H cap. So yeah, since this is at 25 degrees Celsius water, so we are considering this to be 0. Let me call this as H1. This is not there. Now there's one thing particular about the mixtures, that since everything is given in terms of moles of solvent, so yeah, so here 44.4 kilomole are there, but here some H is there which I'm not taking. The H will be accounted for in the HCl aqueous. So yeah, you are having 54800 moles and some H. Let me not call this H3, H2. Okay, so we know that delta H is H out minus H in, right? Which is H2 cap into 54800 minus H in. H in is H1 into 54800. 548 double, no, sorry, it's 5480. Numbers you can see, but yeah, let me talk about the recipe to solve the question. So H1 is H1 is good enough. H1 you just do, since the reference state is 25 degrees Celsius. So basically you are just heating HCl gas from 25 to 100, so 25 degrees Celsius to 100 degrees Celsius. Sorry about that. 100 degrees Celsius CP DT. Yeah, so let's resume. We were heating HCl from 125 degrees to 100 degrees. So CPDT, you'll get some value, some X, if the CP value is given. Now the main thing is H2. Okay, so what to do with this H2? So basically, what you're doing is you are mixing those things, right? You're mixing them at 25 degrees Celsius. So basically, you are mixing at water temperature of 25 degrees Celsius, and then you're heating the mixture up to 40 degrees Celsius. So these are two different steps. This can be given directly by delta H mixing at 25 degrees Celsius. So this is given over here. One thing you might be wondering that HCl is at 100 degrees Celsius, why we are not bringing it down to 25 and then doing the mixing? So the answer for this is when you do this thing, when you do this step, it is already accounted for. So basically, when you are doing this, you will have minus H1. So it's equivalent to doing cooling down HCl from 100 to 25. So you don't have to account for that. You just account for H1 here, 0 here, and directly do for H mixing. This will do. So you are having 69 point whatever value is there into the number of moles 5480, and then what you're doing, you're heating the mixture to 40 degrees Celsius. So here you cannot heat water and HCl separately. Water and HCl CpCp values you cannot do separately because HCl is actually a vapor at that temperature. But here we are considering it as an aqueous solution. So basically, you need to find, you need to have the Cp of solution to solve this problem. That will be given in the question. So you just heat the 25 to 40 Cp of solution of the specified concentration dt. This is temperature, so capital T. And then you do H2 minus H1. As simple as that. So yeah, that's all about enthalpy of mixing. Now let's talk about enthalpy of reaction. So yeah, in reaction, enthalpy heavily depends upon temperature. So you always need to take care about reference temperatures. And one basic plot which you would have learned in your JEE days is this is enthalpy. So this is an endothermic, this is exothermic. Just to say that endothermic, the final is at higher enthalpy than the initial. So delta H is greater than 0. Here delta H is less than 0. Things like that. And then there's one small thing I would like to mention here. Let's say you have a reaction 2A plus 3B gives 4C plus let's say 3D. Okay. Now I'm given that delta H of reaction is equal to let's say 100 kilojoule per mole. Now the question comes that per mole of what? So it's actually kind of per mole of equivalent. So how do you call that? Let's say I want to find heat of reaction per mole of A. Then you'll do 100 by coefficient of A, which is 2. You'll get 50 kilojoule per mole of A. Let's do it with let's just C. So 100 by 4 coefficient of 4 C, which will give me 25 kilojoule per mole of C. That is just about the convention used. You need to keep this in mind. And then when we are specifying delta H for a reaction, again, the coefficient, the as you see from here, if you multiply by 2 everywhere, let's see here 4, 6, 8, and 6, then delta H of reaction will be multiplied by 2. So yeah, so that thing you need to keep in mind that you need to have a stoichiometric equation for delta H of reaction. Then it's like if A is in liquid and you have the same reaction with A in gas, so delta H of reaction will be different for both because the evaporation step will also be incorporated in the second case. That is one thing. Now we have heat of formation. Heat of formation definition, you all know that a reaction in which the final product is created from the elemental forms, from the elemental stable forms of that product, from that molecule. So let's say we have H2O forming. So here H2 plus half O2 at the reference state. So let's say reference state is in general 25 degrees Celsius, 1 atmosphere. At these H2O, H2 is a gas, O2 is a gas. So you do this to get H2O. So yeah, delta is formation. That is one thing. Now there's something called Hess's law. What Hess's law states that if you are going from path A to part B, sorry, a product A to product B, or you are going this way, so delta H calculated this way, or you go from this way to here, delta H will be same. That's about Hess's law. Then a heat of combustion, again, like completely combust the things. So how much heat is required? That is heat of combustion. And whenever you're given a question, there is a general method. First thing you do is a material balance. Then second thing, you see that what is the reference. Third, after finding a reference, you do the enthalpy table as we had drawn here, kind of a neater one, but yeah, you need to draw enthalpy table, and then finally get delta H. So there's a small uh, catch in this. There are two ways of solving. Either you do with delta H of reaction, or you can proceed with H of formation. So in delta H of reaction, you take the reference. You take the reference to be molecules or the compounds at some standard temperature. And in this, whenever you draw a table, you'll get delta H equals to summation H out minus summation H in plus delta H of reaction. And when you do with this, here reference will be elements at 25 degrees Celsius. Like for H of formation, the reference states, whenever you define heat of formation, the reference states are elements, pure elements at some temperature and pressure. So yeah, 25 degrees Celsius, 1 atmosphere, the general one. And in this, you'll get delta H equals to delta H out minus delta H in. You won't have the delta H reaction term here, because here the bond formation and the bond breaking are already accounted for, whereas when you're considering this method, you have to account for it separately. So yeah, maybe solving one or two questions from the book for this will be a good idea. Okay, so that's all for this last video, and hope you do well in your exams. All the best.